All right, this next example 5, we're going to sketch a graph that satisfies this information. So here, some of the information is given in terms of absolute values, which might be a little confusing. So it's going to be useful to go ahead and sort of parse this a little bit, a little bit more. So, for instance, let's take a look at this first, not this, the second bullet point here. So this second bullet point says absolute value x less than 1. So this means the distance, the size in x is less than 1. So this would mean if we look at x equals 0, we can move to the right or to the left 1 unit of distance. So this is really equivalent of saying x is between -1 and 1. That's what that's saying. Similarly here, this is saying the distance from 0 is between 1 and 2. So if you think about this on a number line, if this is 0, here's 1, here's -1, -2, 2, we want this distance here from 0, that's what absolute value of x is, its distance from 0, to be between 1 and 2. So this means essentially this range of values and this range of values. So you can see how this notation is a lot more compact than having to write this inequality and this inequality. But just to be clear, this is really saying this is equivalent to -2 less than or equal to x less than or equal to -1 and or I should say x between 1 and 2. As long as x satisfies one of these two inequalities, this inequality is satisfied, and therefore we apply this. Okay, this is saying that the distance from 0 is greater than 2. So this is really on our number line here. If you think about it, here's 0, 1, -1, 2, -2. We're talking about that as this goes to positive infinity and this side goes to negative infinity. So really we're saying x less than -2 or x greater than +2. That's what this inequality simplifies into. So there you go. And this one is straightforward. Okay, so I just wanted to take the moment to parse that extra information in case you're having trouble with that. All right. So, essentially, what we do know is that it looks like 1, 0, 1, -1, 2, -2 are going to be important values based on what we just talked about here. So if we're thinking about a number line here, it seems like important things are to keep track of are the regions, are these regions less than -2, between -2 and 1, between -1 and 0, between 0 and 1, between 1 and 2, and greater than 2. So 1, 2, 3, 4, 5, 6 separate regions to consider. So that's a lot here. So what we do know here is that, let's go one by one. So we do know that the first derivative, what I'm going to do here is I'm going to put first derivative information up here. Let's do this right here. And second derivative information down here. Okay, so yeah, make these up here a little bit more. All right, so like I said, it's good to be organized. So what we do know is that when the first derivative is equal to 0 when x is equal to 1 or negative 1. So for first derivative, I'll do blue, so I know that this is 0 and this is 0. Okay? Now we do know that between negative 1 and 1, the first derivative is less than 0, so it's negative. So in this region here, we actually have negative first derivative. So negative, negative. I'm going to write information within each region. I don't want to leave it blank. Okay. So then, so far, let's see, we've taken care of the first bullet point, the second bullet point. The third bullet point is that if we are between negative 2 and 1, so right here, or between 1 and 2, so right here, if we're in either of these two regions, the first derivative is positive. So this would mean positive, positive. So now the first derivative is actually, they give us a precise value, not just that it's negative, but it's equal to negative 1. So for anything here or here, the first derivative is negative 1. So I'm going to put that in a little circle just so it's like special information. So now second derivative information. Actually, before we move on to second derivative information, let's just notice here that we don't have information about 0, x equals 2, or x equals negative 2. But we can use what we know already about other neighboring information to try to fill in the gaps. So let's take a look at negative 2 first. Negative 2, we see that the function goes from a derivative value of negative 1 and it goes to 0. Oh, sorry. I meant to say from negative 1 to positive. So as we cross over negative 2, we go from negative 1 to positive. Well, if we go from negative 1 to positive, this can't be 0 actually. Why is that? Well, we're assuming that this function is always a slope of negative 1. So that means if we were to graph this, the slope is something like this, negative 1 slope. How can we go from a negative 1 slope to a positive slope smoothly? We can't. That means, right, if this were 0, then that means, and if it were differentiable, that means next to it, at a point really close, like negative 2.0001, we would expect the slope to be perhaps maybe negative 0.001, and then the further away we went, this slope here would approach negative 1. Right? It would transition from 0 to negative 1 smoothly. It doesn't. It's always negative 1, and then suddenly on the other side of this x equals negative 2, we now have a positive slope. So this is sort of indicating that the derivative does not exist at x equals negative 2 because we jump from a negative to a positive, but there's no way to go from negative 1 to a positive unless we go through values between negative 1 and some positive number, which would include values like negative, negative 0.9. But we don't hit that. And we don't hit negative 0.8. We don't hit any of these intermediate values. So that means it has to have a rapid transition, an instantaneous transition. So they don't specifically say what the derivative is at these locations, so we are free to import it as long as it doesn't contradict with other information. So we're going to go ahead and write dne here, and the same argument will be used over here, so we'll say dne for the derivative as well. All right, now here in the middle, we go from negative to negative. So it could be the case that we do have something like decreasing, right? We could have something that's like decreasing 0 and then decreases again, right? we could have that. The other possibility is we have something like this, where we actually right here go vertical for a second, in which case the derivative would not exist as well. So really, it depends on what the concavity is. If the concavity is concave up, concave down, then we could say that the first derivative was 0. But if we have something that's concave down to concave up, then this would mean the derivative does not exist. Those are the only two options. So, yeah. Yeah. Yep, there's no way to tell exactly which case we have unless we go ahead and take a look at the concavity. So we're going to have to put a big old question mark there for now until we come back and look at the concavity, which we'll do now with the second derivative. So the second derivative, we're told that when x is between -2 and 0, so right here, the concavity is downward because the second derivative is negative. So this is concave down. So I'm going to say concave down, concave down. We have an inflection point at 0, 1. So, so this means we know that the value, the y value here, is actually given to us. So this is 0, 1 as a point. We know that this has to be an inflection point. So that means this has to, the second derivative here has to be concave up on this side. So again, just because we know we go from concave down to concave up, concavity can switch. Doesn't necessarily have to be, second derivative might not exist. We're not for sure right here. So the second derivative could be 0. It could be something else. So we don't know for sure here. But because we do know that we go from concave down to concave up, we can actually answer this question. So concave down would be something like this. Concave up, something like that. So here, it's a vertical tangent, so that derivative does not exist. So we can go ahead and replace this question mark with a D and E. Okay. That's great. Now, we also know because the slope of the tangent line is constant and equal to -1, we know that here and here, there is no concavity, because if our slope is constant equal to -1, that means we just have these kinds of lines. That's a slope of -1, slope of -1. So slope of -1, this is neither concave up nor concave down. So it's not that we're missing information. There's just no concavity in this region. Okay. Now here, 1 and 2, we're not given anything specific to work with. So it may very well continue being concave up. So I'm going to put a question mark / concave up. Let's see if we can satisfy our graph now. So what I'm going to do here is essentially piece together what we have. So what we do know is that our graph has a slope of -1 for a little bit of time. So there we go. And then we know that that was right here. Now we're going to increase in a concave down way, so that would be something like this. So that means, so it's curving, something like that. Okay, so that's right here. Then we flatten out, so the horizontal tangent, and then we decrease concave down. So that checks out, so we'll kind of do something like, oops. Okay. So there's our horizontal tangent at the top. And then we have, let's see, we're going to keep going here. We're going to decrease concave down, and then we're going to concave up and decreasing. So essentially, we're going to keep going. There's our point of inflection right here. And then we're going to start doing that until we get to the horizontal tangent, which means we flatten out for a second right here. And now that we're there, we have to, so that's where we are right here. So now we have to increase, so you have to increase, and it doesn't say anything. So can we, it doesn't say, it does say the derivative exists here and is equal to 0. So we can't go from, if we're going to increase, there's only two ways we can increase. We can increase like this. That's concave up. We can increase concave down, but that would then mean that, do you see how the derivative, like, it couldn't exist here? But we know that the derivative does exist and equals 0, so that means it has to be in this concave up way, so concave up. Until we get to 2, and then we're going to have a, excuse me, we're going to have a slope of -1. So let's go ahead and say we are increasing, and then let's just say right here at some location, we then just start to go, these lines should be parallel, so there we go. So now what else do we know? We do know that we have an inflection point at 0, 1, so our inflection point right here, we know the y value is 1. So we're not told any other information, so I'm just going to go ahead and draw the horizontal axis. And then with this point is 0, 1, we know that the y-axis has to go right through there. There we go. So labeling things, we have 0, 1, it's our inflection point. We have -1, we have -2, we have 1, we have 2. That graph satisfies it.